Welcome back to Neural Intel. Today, we're diving deep into a really core challenge in the world of large language models.
Right.
How to get them to continuously learn new stuff without, forgetting everything they already know. This thing called catastrophic forgetting.
Yeah, exactly.
We'll be focusing on the technical side, the details, and what it all means.
Absolutely. And think about why this matters. I mean, practically. If you have an enterprise AI assistant, it needs to learn about new products, right? Or maybe a medical model keeping up with research.
Constantly retraining from scratch. Just not feasible.
No way. The computational cost is just huge.
Right.
So this is where continual learning really comes in. It's critical.
And the source for our deep dive today, it's a really interesting paper from Ark Schoaf. It's called Sculpting Subspaces, Constrained Full Fine-Tuning in LLMs for Continual Learning. What jumped out at me is their method seems, well, pretty technically solid, but also scalable.
That's what's exciting. The core idea they're exploring is using adaptive singular value decomposition, SVD.
SVD, right?
Yeah, as a way to sort of intelligently manage how the LLM's internal parameters get updated when it learns new things. It's surgical, not just broad changes that mess things up.
Okay. So let's get right into the problem itself. Why does this catastrophic forgetting happen in the first place? Why does teaching an LLM something new often make it, well, stumble on the old stuff?
The fundamental issue is really how interconnected everything is inside the neural network, the representations. When a model learns task A, it adjusts all these parameters, right, to encode that knowledge. Then task B comes along. The adjustments needed for task B can just overwrite or interfere with those task A encodings.
Okay. Like painting over an existing picture almost.
Kind of, yeah. Or maybe like adding a new floor to a building, but the foundation for the old floors gets destabilized. It's all connected.
Makes sense. So before this new SVD approach in the paper, what were people trying? What were the existing strategies? And I guess where do they fall short? Parameter-efficient fine-tuning, that's been big, right?
Oh, yeah, definitely. Techniques like adapters, and especially LoRa low-rank adaptation, they've been really popular.
Right.
The basic idea there is you freeze most of the huge model, and you only update a small set of new or existing parameters.
So you limit the damage, basically.
Exactly. It helps mitigate the forgetting because you're not changing the core model as much.
Okay. Sounds promising.
Yeah.
But obviously not the whole story. What are the downsides?
Yeah.
The limitations?
Well, one big thing is expressivity. By only tweaking a small number of parameters, the model might not be able to fully capture all the nuances of the new task. It's like trying to write a complex novel with a very limited vocabulary.
Okay.
And there's another potential issue, especially with some methods, scalability. Sometimes you need to add new parameters for each new task.
Oh, right. So task after task, the model just gets bigger.
Potentially, yeah. More parameters mean more memory, maybe slower inference. It doesn't scale indefinitely.
The paper also mentions a couple of LoRa variants, OLoRa and InFlora, orthogonal and interference-free LoRa.
Right. Those are newer twists on LoRa. They try to be smarter about the updates. The goal is to make the updates for the new task more orthogonal, like at a right angle to the updates from previous tasks.
Trying to keep them separate in the parameter space.
Exactly. Another way to minimize interference. But, they still face some of the same fundamental trade-offs, that balance between expressivity for the new task and avoiding forgetting, plus the parameter growth thing.
Gotcha. And then there was model merging mentioned briefly, too.
Yeah, that's a totally different philosophy. Instead of one model learning sequentially, you train separate models for each task.
Like one expert model for task A, another for task B.
Right. And then you try to somehow smush them together and merge their weights.
Sounds complicated.
It is. Training multiple full models is expensive, obviously. And then figuring out how to merge them effectively without hurting performance on any of the tasks. That's really tricky. Often needs a lot of fiddling.
Okay, so that sets the stage. We see the problem, the previous attempts. Let's dive into this paper's core idea, the adaptive SVD approach. What's the big innovation here?
The absolute core is using singular value decomposition, SVD, to understand which parts or which, let's say, directions within the model's weight matrices are most important.
SVD. Okay, refresh my memory a bit. How does that math help figure out what's important?
So SVD is a way to break down a matrix. You get these singular values and corresponding vectors. The key insight, or hypothesis really, in the paper is that the directions linked to the large singular values are the ones that are crucial for holding on to the knowledge the model already has.
The important stuff it learned before.
Precisely. And conversely, the directions linked to the small singular values They're seen as less critical for the old knowledge, maybe redundant.
Ah, okay. And this is where it gets really interesting, right? It's not just using SVD, it's how they use this info.
Exactly. That's the clever part. They adaptively identify these less critical, low-rank directions, the small singular value ones, and they say, okay, let's use these directions to learn the new task.
While protecting the other ones.
Yes, while actively protecting the high-rank directions, the large singular value ones, because those are assumed to hold the vital prior knowledge.
Okay, but how do they know which layers are more important for remembering? It can't be the same across the whole massive network, surely.
Good question. No, it's not uniform. They actually figure out an important score for each layer.
How?
They look at the cosine similarity. They feed data from an old task through the model and measure the cosine similarity between a layer's input and its output.
Cosine similarity.
Yes.
So if the input and output are really similar for that layer on old data.
High similarity suggests that layer is mostly just passing information along, preserving it, not transforming it much.
Ah, okay. So preserving layers are probably important for remembering.
That's the idea. The paper argues these preservation-focused layers are more critical for retaining old knowledge. Lower similarity means more transformation, maybe more plasticity, more room to learn new things there.
And these layer importance scores then feed into how much SVD protection each layer gets.
Exactly right. The score guides how many of those important high-rank components tied to the big singular values are kept safe in that specific layer. More important layer, protect more components.
That sounds much more nuanced than a global approach. Very granular.
It is. It allows for adaptivity.
So to make this adaptive thing concrete, the paper introduces two hyperparameters, right? Minimum retention ratio, MITR, and target retention ratio, TRR. What do those control?
Okay, so the MITR, minimum retention ratio, that's like a safety floor. It guarantees that even the least important layers still keep a certain minimum fraction of their high-rank singular vectors. You don't want to completely throw everything away anywhere.
A baseline protection.
Yep. And the TRR, target retention ratio, that's the ceiling. It defines the maximum fraction of important vectors that the most critical layers will hang on to.
So MITR is the floor, TR is the ceiling. How do they pick the level for a specific layer in between?
They use a pretty simple formula. It just interpolates linearly between MITR and TRR based on that layer's importance score, IL. The actual retention rank, where L for layer L is RL, is MITR-RR,
Okay.
plus IO, TRR-LR.
Ah, okay, I see. So if the importance IL is high, closer to 1, then RERL gets closer to the target, TRR, more retention.
Exactly.
And if IL is low, closer to 0 REL, stays near the minimum, Mr. less retention, more room for new learning.
Precisely. It allows that fine-grained layer-by-layer control over the trade-off.
Very elegant. Okay, so they've identified the important high-rank subspaces to protect in each layer. Now, how do they actually train on the new tasks without messing those up?
This is the other really crucial part. Orthogonal gradient updates.
Orthogonal updates. Sounds mathematical again.
It is, but the concept is key. So when the model learns the new task, it calculates the gradients the parameter updates like normal.
Okay.
But instead of just applying those updates directly, they project them. They force the updates to lie primarily within that low-rank subspace, the directions identified as less critical for old knowledge.
Projecting them. So redirecting them.
Kind of. Imagine you have your protected high-rank directions. The calculated update might want to push into that protected space. The projection step basically says, nope, you can't go that way. It redirects the update so it's orthogonal at a right angle to those protected directions.
Like trying to draw on a piece of paper, but only allowing strokes that are parallel to the bottom edge, not perpendicular to it, if that edge represents the protected knowledge.
That's a decent analogy, yeah. By making the updates orthogonal to the important old directions, you minimize interference. You don't scribble over the important parts.
But critically, within the allowed space, the low-rank space, the model can still make significant updates.
Yes, that's a major point. It's full parameter fine-tuning within that allowed subspace. This maintains the model's expressiveness for the new task, which is a potential advantage over methods that just freeze most parameters or use very small updates.
So it's really about finding this sweet spot, plasticity to learn new things, but stability to remember the old.
That's the goal. And the results they show suggest they're doing a pretty good job of hitting it.
Right, let's talk results. They tested this on standard benchmarks, you said.
Yeah.
What did those tests look like?
Yeah, they used standard setups. One was a sequence of 5 tasks, another a longer, tougher sequence of 15 tasks. And they didn't just use one model type. They tested on T5 large, which is an encoder-decoder, and also Llama 2 7B, a popular decoder-only model.
Good variety. And the main metric was?
Average accuracy, or AA, across all the tasks learned so far. So after learning all 15 tasks, how well does it still do on average on all of them? It's a good measure of overall knowledge retention.
Makes sense. And how did their methods stack up?
Pretty impressively, according to the paper. They claimed state-of-the-art results beating strong baselines. They specifically called out OLORA, that orthogonal LoRa we mentioned.
Okay.
They reported gains of up to 7% in average accuracy compared to OLORA. On the 5-task T5 setup, it was close, like 75.9% for them versus 75.8% for OLORA.
Okay. Basically tied there.
But on the harder 15-task setup with T5, the gap widened. Their method hit 71.3% AA, while OLORA got 69.6%.
Okay, that's a more noticeable difference. Nearly 2% absolute gain on a tough benchmark. That's significant.
It is, yeah. And they had other interesting results, too.
Like what?
They used another benchmark called TRACE with the Lamine 27B chat model. This one has more diverse instruction-following tasks. Again, higher average accuracy for their method, 48.4% versus 41.3% for OLORA.
Wow, that's a big gap, over 7% absolute.
Yeah. And interestingly, they also saw better backward transfer on TRACE.
Backward transfer. That's when learning task C actually improves performance on task A, right?
Exactly. It suggests the model isn't just not forgetting, it might actually be refining its understanding in ways that benefit older knowledge, too. That's pretty cool.
That is cool. It implies a more synergistic learning process.
Yeah.
Did they check if this fancy subspace stuff hurt the model's general abilities?
Good question. They specifically looked at that. They report that general linguistic skills, instruction following accuracy, even safety alignment were maintained. They point to tables 3 and 4 in the paper for the evidence on that. That's crucial for practical use, obviously.
Absolutely critical. Okay, strong empirical results. Does the paper offer any theory on why this works so well? Why SVD and orthogonality are the right tools?
They do provide some theoretical justification, mostly in the appendix. It involves looking at the loss landscape using a second-order Taylor expansion.
Okay, getting deep now. Yeah.
The core theoretical idea is that to minimize forgetting, you really want to avoid changing the parameters and directions where the loss function changes most sharply. These are directions associated with high eigenvalues of the Hessian matrix.
The Hessian, that second derivative matrix, sounds computationally nightmarish for LLMs.
Exactly. Calculating the Hessian and its eigenvalues for these models is basically impossible in practice. It's way too big.
So how do they connect that to SVD?
They argue, based on some prior work and empirical findings, that the top singular vectors you get from SVD, the ones corresponding to the large singular values, act as a good, computationally feasible approximation for those high Hessian eigenvalue directions.
Ah, okay. So SVD gives an efficient way to find the directions that are most sensitive, the ones you don't want to mess with.
That's the intuition. By preserving those top singular vectors adaptively, they're effectively approximating the protection of those critical directions in the loss landscape.
Does this lead to any formal guarantees, like mathematical bounds?
They derive a hierarchy of theoretical bounds on forgetting. It basically shows their adaptive SVD method should, in theory, forget less than a simpler fixed-rank SVD approach, and definitely less than just doing full fine-tuning without any constraints. So theory supports the approach.
Okay, that adds weight. What about their basic assumption that the low-rank directions are actually redundant or less critical?
Yeah.
Did they test that directly?
Yes, they did some neat validation experiments for that. They took pre-trained models and just chopped off the components corresponding to the smallest singular values, pruned them away.
And what happened?
Performance dropped very little, even when they removed a significant chunk of these low-value components.
Really? That strongly suggests those directions do have redundancy.
Exactly. It supports the idea that you can repurpose that subspace for new learning without causing major harm to the existing knowledge. They detail this in Appendix A.2 and Figure 5.
That's pretty convincing evidence for the core premise. Did they also do ablation studies, like removing parts of their own method to see what breaks?
Oh yeah, standard practice. They did a couple of key ablations. First, they messed with their own retention ratios, Masurta or Chirkar. They made them much lower, meaning they preserved less information. Performance dropped significantly. It showed that getting that rank estimation right, how much to preserve, is really important. Be too aggressive, discard too much, and forgetting shoots back up. You need that adaptive balance.
Makes sense. What was the other ablation?
They turned off the orthogonal projection. So they still identified the low-rank subspace, but they allowed the gradient updates within that subspace to go in any direction, not forcing them to be orthogonal to the high-rank space.
Oh. I can guess what happened.
Yep. Catastrophic forgetting came roaring back. It really highlights that just finding the subspace isn't enough. You need that orthogonal constraint during the update step to actively protect the old knowledge.
Wow. Okay, so both the adaptive rank selection and the orthogonal updates are essential components.
Seems so, based on their tests.
One last practical point. Scalability. Especially for learning many, many tasks over time. How does this method compare?
That's actually one of its big selling points. Because they're working within the existing model parameters, just reallocating how different subspaces are used, the total parameter count stays fixed. Unlike some PFT methods that add new modules per task.
Exactly. No growing parameter budget. This makes it inherently more scalable for very long sequences of continual learning, which is crucial for many real-world applications where learning is truly continuous.
Okay, let's try and wrap our heads around this. What we've looked at today, the Sculpting Subspaces paper, it feels like a really smart, innovative attack on a fundamental problem for LLMs in the wild.
It really does. It offers a way to keep these incredibly powerful models learning, adapting to new information, without that disastrous forgetting we've seen plague earlier approaches.
And what's really key here, for our technically minded listeners, is that it seems to achieve this continual learning while letting the model use its full capacity, that full fine-tuning, within the allowed subspace and without adding parameters constantly.
Right. That combination of adaptive SVD to identify what's important, and then the orthogonal updates to protect it while learning new things. It's a sophisticated way to manage that plasticity versus stability trade-off. So the takeaway seems to be, we might be moving towards AI systems that are genuinely more adaptable, that can learn throughout their lives, whether it's for an enterprise assistant needing constant updates or a scientific model keeping pace with research.
And the fact they showed it works well while maintaining general abilities and safety. That's huge for actually trusting these systems in deployment. It's not just a theoretical trick, it seems practical.
So this deep dive definitely leaves us with something to think about. For you listening, maybe consider, how could these improvements in continual learning change how we build and use AI in different technical fields? What new things become possible if models can reliably learn and remember over the long haul?
Yeah, what doors does this open?
For anyone wanting to really get into the weeds, the full paper is on ArcSev. We'll put the link in the description, but it's arcsevv.org, PDF 504.07097V1. Definitely worth a read if you're into the nitty-gritty technical details.
It's a dense read, but yeah, fascinating stuff.
Well, thank you for joining us on this technical deep dive into continual learning and sculpting subspaces. We hope it gave you some valuable insights into where this field is heading.
Yeah, it's an exciting space. Stay curious, everyone, and we'll catch you next time on Neural Intel. And remember, for the latest AI and ML research updates, check out our webpage links in the bio.